So in this video, I'm going to finish the 4.3 through 4.5 lesson that we started last time by doing more or less the second half, which is your favorite thing, I'm sure, two-column proofs in order to prove that two triangles are congruent to each other. This ends up not being too bad as far as proofs are concerned. It's actually a lot easier than what we did a couple classes ago because we learned shortcuts for doing this. So we don't need 6 congruent statements anymore. Most of the time we can do it in 3, which is nice. The 3 that worked last time were ASA, SSS, ASA, and then AAS/SAA. One of the ones that didn't work was ASS. And before we actually go on to prove or to talk about how to prove two triangles congruent in a two-column proof, there's one more that we're going to learn about, one more shortcut, which is nice. And to go anywhere with it, we have to kind of understand why, again, ASS doesn't work. The diagram to the right shows a counterexample where I have the ingredients of a pair of angles and 2 pairs of sides positioned in a way that's ASS rather than SAS. Right? Angle P and angle A are congruent and not in between the 2 pairs of congruent sides. Yet this doesn't demonstrate that it's guaranteed for the 2 triangles to be congruent because this one on the right, QPR, is clearly not congruent to the one on the left. Like, it looks like this one is an obtuse triangle and this one is an acute one. If I had taken this angle R, though, and kind of moved it over here, in other words, kind of like rotated segment QR by like swiveling it across angle Q, I'd end up with a triangle that actually is congruent to ABC. This one would be congruent to ABC. But that's not how the side ended up being. The relationship between these two sides, the old QR and the new one that I drew in right there, is that it seems like this side kind of reflected across, more or less, a perpendicular line. We can see it kind of reflected. An example of when ASS, or special kind of ASS, actually will work is if that second pair of congruent sides actually is a vertical line, because then it really has nowhere to reflect to. Think about if the 2 marks were on the vertical line. Well, then I'd have a diagram much like down here, where there's ACB and there's DFE. It is going to be the case, even though it's ASS, that these 2 triangles are congruent. And we can justify that for a couple reasons. One, because the counterexample of getting another triangle that's reflected across a perpendicular line doesn't really work, because the 2 sides are already perpendicular, so there's nowhere to reflect it to. The other way, the more sensible way to think about it, is to think about how the Pythagorean theorem works. It's a right triangle now. These are right triangles, so I can use the Pythagorean theorem. Imagine if these side lengths are 10 and 8. If I solve for CB and if I solve for EF in these, well, there's only one way to satisfy the Pythagorean theorem with something squared plus 8 squared equals 10 squared, and that number is 6. 6 squared plus 8 squared equals 10 squared. And if both of these sides rather end up being 6, I more or less just have SSS. So as it turns out, I can have a special ASS theorem. We don't call it that, though. We call it hypotenuse leg, where the A stands for a right angle, and these 2 S's are the hypotenuses, hypoteni, I don't know, and just some other leg in the triangle. So remember that hypotenuse is a term that's specifically reserved for right triangles. It is the thing that's opposite the right angle. So this is just one more thing to our repertoire of proof tools. Here is again the 4 from last class, as well as hypotenuse leg, which again works only with right triangles. The ones that do not work, which do not fall for the trap of trying to use these because they don't prove congruence, are AAA, and then ASS, and not the special kind. So I'm going to dive into this. I'd recommend watching me do this first one, and then after this, maybe pause the screen and try to do the rest yourselves before I end up giving away the answers. My advice before I even begin this one, or any proof really, is to look at the diagram that you have, and before you hit the table, start to mark it up with stuff that you know to be congruent, either because it's given to you or because you can deduce it. That way you can kind of give yourself some stuff to work with, come up with a 3-letter shortcut, and then use that in your 2-column proof. Really, we should be thinking of the logic for proving these 2 triangles congruent first, and then really just articulating what we already know to be true in the diagram. So for example, I know Ki is congruent to IE, that's 1 pair of S's already. I know that these are both 17, so If they both measure 17, then the segments have to be congruent. That's awesome. And then the third thing to do in this diagram, since we're not even given a line of given information, there's not too much going on here other than IT being a shared side, therefore it's congruent to itself. And then I have an SSS sort of diagram where I know that KIT is congruent to EIT via that three-letter shortcut, via SSS. So in terms of formalizing everything, it doesn't really matter what order I lay it in the table with. I'm just going to put it all down. And then once I have my three ingredients, that's enough to conclude, all right, these triangles are congruent. So that was given to us. Ki is congruent to IE. It was given, and this is a little bit of a long way of doing it, even though it's obvious, but we know it was given to us that these sides are 17. We then deduce, even though it's not a huge deductive gap, that because they're both equal to 17, they're equal to each other. And that's either transitivity or substitution, depending on how you want to think about it. Thus, if their lengths are the same, then the segments themselves are congruent. And then the third thing was the reflexive property. It's congruent to it. And then I could see, especially if you label these things, I wasn't saying to do that as a joke. That's super helpful, actually, that this is just triple S. Triangle KIT is congruent to triangle EIT because of SSS. I labeled it this way because it's a kite, and also there's our gnome friend, whatever his name is. Again, so after you've seen one, hopefully you have some idea of how to go about the rest of them. So if you'd like to right now, pause the video and try to figure this out yourself. In this milk one, though, yes, it spells milk. I'm given that M is congruent to L. That's cool. I'm given that these two angles are right. Thus, we could again make the short logical leap that they're congruent to each other. And also, I can see that segment IK is congruent to itself. So I'll throw this mark in there for the reflexive property. Believe it or not, that's actually all we need in order to show that these two triangles are congruent. I have two pairs of A's and an S. So if I decide to hit the table about this, I'll lay out the first given. That's fine. The second thing I can conclude, it doesn't really matter the order in which I do it. Like these two steps are interchangeable, but I could say that IK is congruent to IK. That's the reflexive property. I know that these two angles are right. That's what's given to us. Therefore, I can say that they are congruent by the right angle congruence theorem. If you somehow wanted to condense these two lines into one line, I'm actually okay with this because this is tedious. But one thing that I do want to point out is that the way I've put this in the table, it makes it look like I'd be using ASA to justify this statement here, that these two triangles are congruent. However, the way I lay it in the table is potentially interchangeable and different for every student. So that's actually, it actually doesn't matter in terms of the three-letter shortcut I would use to justify this statement. What matters is the diagram and their relative positions in the milk diagram here. It looks like, because the pair of congruent sides, even though it's just one side, is not in between the two pairs of angles, the acute angle and the right angle. So I would expect then, because my side is not in between the angles, for the S to not be in between the two A's. I'd expect it to be on the outside of the two A's, which would be AAS. I know they both work, so it seems like not a big deal to make this distinction, but it actually is quite important. No! Phone call, sorry. This is Bowtie, our old pal Bowtie, except this time I've given you less information, and we can still actually prove it more quickly, which is really nice. Again, if you want to pause it and take a minute to go at it yourself, that's fine, but I'm just going to go right about now. If I know that O is the midpoint of TW, based on what it means to be a midpoint, that is going to cut a segment into two congruent halves, that tells me that TO is going to be congruent to OW. I can make the same conclusion about the fact that the same point is the midpoint of BI instead. So I can say BO is congruent to OI, because that's what it means for O to be a midpoint of the segment. And then since I'm out of givens, I'm going to have to turn to the diagram and see what else I could deduce. It looks like there's no shared segments, so that's not going to work out. But what I do see is that I have a pair of vertical angles, angle BOT and angle IOW. So I can acknowledge that in the diagram, and really, if I'm paying attention, if I'm labeling my stuff well, I'm done with the problem, because that was my third pair of congruent pieces here, I should say, corresponding congruent pieces. And I can now kind of hit the two-column table to organize these thoughts a little bit more articulately. So again, the order doesn't matter, but I might as well start with the given. O is the midpoint of T dubs, and therefore TO is congruent to O dubs, because that's what it means for O to be a midpoint. That's the definition of midpoint. The next two lines are more or less the same, because O is also the midpoint of BI. So BO and OI are congruent to each other. Then we had the vertical angles making up an A. And again, despite the fact that this spells out SSA, we know it better to be SAS. One, because SSA doesn't work unless it's the hypotenuse leg theorem. And in this case, the A, or the pair of angles, is in between the two sides, which is to say, when the 2 mark and the 1 mark sides meet up, they meet up to form these pair of congruent vertical angles. Therefore, this is SAS. In this case, on the next page, pause it right now if you want to try it, but I'm going to go right now. The C is congruent to the N, no big deal. This is a pair of vertical angles once again, awesome. And then if CO and ON are both equal to root 8, then they're equal to each other. Thus, the segments themselves are congruent. So once again, if I were to hit the table here, C is congruent to N, that's given. There's the vertical angles. There is the given fact that both of these measures are root 8. Therefore, their measures are equal, their lengths are equal, be it the substitution or transitive property. And then based on the definition of congruence, they're congruent to each other. So I left this one blank over here so that we don't lose sight of the fact that it matters what order we state our vertices, because we have to do it in such a way that shows what parts are congruent with what from one triangle to the other. So triangle 1, if I'm looking at corresponding pieces, it looks like it would be congruent to what looks like W would match up with R. Point O is shared in between them, and it kind of matches up with itself. And then that would kind of mean that N corresponds with C, and that makes sense because angle N and angle C are congruent to each other. So it is the case that triangle 1 is congruent to triangle rock by ASA. Also, this spells crown, and there's a crown. This last example is rather tricky. Again, pause it if you want to. I'm going to give a piece of advice in a minute. So my advice after I mark things up here, I know that CR being perpendicular to RN means, by definition of being perpendicular, that it's going to make some right angles, here and here. I know that CN is congruent to OR. This is a little difficult to show because of the overlap. And then that's the end of the given information. It may not even be clear right away what we're trying to show congruent. CRN, which is this big guy, is congruent to something else. So maybe if I highlight this, it'll be a little more obvious what it's congruent to. And we can probably take a good guess, but we're still short one ingredient in terms of pair of congruent sides or angles. So my advice would be, if the overlap is bugging you too much, draw them separately. I'll call this triangle CRN over here, and then if I kind of detach ORN from it and draw it on the side, pretend I did an okay job of showing that they're congruent. ORN. I'll mark some of these things up again. So I know that these are right angles, where R and N are. I'm told that CN is congruent to OR, and then I'm still short one thing. Well, if there's ever an overlap between the two shapes, that should probably tell me, or that should be a hint, that I'm going to use the fact that the shared side of Rn is congruent to itself. It's a little more obvious up here what it means, or I should say it's a little more obvious in the first diagram that Rn is congruent to itself. A little more obvious in the diagram I drew what this means in terms of showing congruence. I have two pairs of sides and a pair of angles. However, that angle is not in between the two sides. So this is AS, but it's the special kind. So again, there's the given, there's the right angles because of the definition of perpendicular. That's great. And that gives us this congruence statement of CRN is congruent to ONR via the right angle congruence theorem. There's the given of CN congruent to OR. There's the reflexive property with the shared side of Rn congruent to Rn. And then the final step again would be our new pal, hypotenuse leg, with CRN congruent to ONR.